Bismillahirrahmanirrahim. My name is Shahzaib Aslam, and the topic assigned to me was genetic algorithms. Let's discuss a brief introduction about what genetic algorithms are. Basically, the word genetic algorithm has been developed by John Holland, his colleagues, and his students at University of Michigan in 1975. It's basically abstraction of real biological evolutions. Like human beings evolve, the same concept was used in artificial intelligence algorithm, which is based on genetic algorithms. It's like basically when humans we have certain problems, they evolve accordingly. They get the parents get something, or the parents get immune, and that immunity is being transferred into their children. The same process was used in genetic algorithms. It's basically using artificial intelligence or machine learning. Finding the best solution from the sample space of solution is its basic task. In genetic algorithms, we don't find a solution. We already have multiple solutions, or we can say that we have multiple set of solutions, out of which we find the best one. And to find the best one, the thing which we do is like basically if we have sample space of best solution, we will check the solution, we will find the best thing in that solution, and then we will convert it, or we will take the best thing out of it, and we'll combine it with some other solution and take the best thing out of it. Like this, we will combine best of each and everything, and then we can move toward a good and a better algorithm or solution. Basically, the type of problem solved in this algorithm is the complex problem. The complex problems are solved using this algorithm. The simple problems can be used by using other algorithms too. But when we are using genetic algorithm, it's very obvious that the problem we are going to solve is very complex. Generally, NP-hot problem are solved using this, or we can say this is an example of traveling salesman problem that can also be solved by using genetic algorithm. Okay, about the complexity of what problem or which type of problem should be solved under genetic algorithm, then we can say the exponential time complexity should be solved under genetic algorithm. Now, talking about working of genetic algorithm from a group of individual or chromosomes, the best will survive. It's about the survivor of the fittest. Like in current scenario, we are facing a COVID-19 situation. That's a new thing which human have faced. So what is happening? The people who are infected and get treated, they get immune, or we can say that they somehow develop some sort of immunity. And if this is being repeated multiple times, then human body will evolve and it will learn how to fight with COVID-19. And once human body has done this, this thing will be transferred from the parents to their children, to their offsprings, and it will continue. That's basically survival of the fittest. And the people who are not fit for that, they are dying. So eventually, what will happen? Human race will become COVID free because all those people who might get affected from corona will die. So this is like the one who is fit will only survive. Okay, then data in search space is known as phenotype. It is encoded and then converted into genotype. It's like basically anything, any data, rough data or raw data is called phenotype, and when it is converted and it is placed in the sample space, in a proper sample space, then it's called genotype. And if the data is decoded again, then it becomes phenotype. It's like basically putting data into a specific format. For example, if I need to solve a mathematical equation, and I need data in integer, so any number which is there would be phenotype, and that number converted into integer for my calculation will be genotype. Okay, this is a flowchart which will be explained further too. The flowchart is basically the start from initial problem. Sorry, initial population. We have the initial population, also known as sample space. Then the fitness calculation is done. Then there is selection, crossover, mutation, and then stopping criteria or terminating point. If the terminating point of stopping criteria is fulfilled, then there is optimal solution, and if not, then we will restart from the fitness calculation. Uh, we will discuss an example later on, but to make it generic or easy at this point, we will discuss all these points: the fitness calculation, selection, crossover, mutation. We will discuss that later in the further slides. But to make a very basic example, I can say that if I have the word make, M-A-K-E, and I want that it should be created from the word take, T-A-K-E. Then how I will calculate the fitness? I will see how many letters in take could be transferred to the make. So these are three letters, A, K, E. So the fitness will be 3. So that's how the fitness is calculated. We will see that in the further slides too. Okay, talking about or discussing about the fitness function, it's basically to check the compatibility. As I said earlier in an example, that we have to see that how much fitness is there in the sample space or in the solution. Okay, the fitness function determine how fit an individual is. By individual, we means that the sample space or the data which we have, how fit it is. The probability that an individual will be selected for reproduction is based on fitness score. So it's like if I have multiple things, for example, when I said that I have to make word from make, so it was like the if I have to I have to create the word make, and I am taking the sample space or individual as take, and the other is A B C D E. So the fitness of E would be 2, and the fitness of make take will be 3. So I will choose 3. Oh, the thing which has fitness of 3, which is take, of course. So that's what the probability is. What it meant by the probability, that which has more fitness score, we will choose that thing. The next thing, selection. The idea of selection phase is to select the fittest individual and let them pass their genes to the next generation, as I discussed in the previous example. But let's discuss another example which is based on binary numbers that we will discuss later in the further slide. Two pair of individual parent are selected based on their fitness score. Individual with high fitness have more chance to be selected for reproduction. That's a common thing. That thing which has more fitness will be taken or will be selected for the reproduction. Talking about crossover, crossover is most significant phase in genetic algorithm. For each pair of parent to be mated, a crossover point is chosen at random from with the genes. This is an example of crossover. The point is chosen at point 3. For example, if the sample space or if the parent 1 A1 has 0, 0, 0, 0, 0, 0 and A2 has all ones, so I chose a random point and that is 3. Okay, then offsprings are created by exchanging the genes of parent among themselves until the crossover point is reached. So we chose the crossover point 3. We did this thing. We replaced the A1 values with A2 and A2 values with A1. And the new offsprings are added to the population. Hence, we get this. So in previous we saw that in A1 all were 0 and in A6 all were 1, and we chose a crossover point and random point which was 3, and we concluded and we found out that okay, fine, now when we exchange the values till that crossover point, that was random point. It was no formula to calculate that 3. It's a random. You can take it 4 or whatever point you want. We have 6 bits here. Anything between 6 bits could be chosen. So when the thing is done, when the crossover is done, we get the result like the bits are shifted. In easy word, if I say the bits are shifted, then there's a mutation. Okay, in certain new offspring formed, some of the genes can be subjected to a mutation with a low random probability. This implies that some of the bits in the bit string can be flipped. So there could be mutation, there could be some different change which is unexpected, which could be unexpected too. Not as, but could be. So before mutation, it was like the thing which we wanted in A5, and after mutation, there's a little bit shift. You can see that in A5 after mutation, there's 1 1 moved between two zeros. So it's 1 1 0 1 1 0. So this is a mutation, which is a change. Sometimes mutation could be good and sometimes mutations could be bad. For example, cancer is a type of mutation. That's a mutation in human DNA and that causes cancer because DNA reproduces itself again and again and again and again. If there's something different or there's some change in DNA, so it will cause mutation. Mutation occur to maintain diversity within the population and premature convergence. This is one of the way why mutation, reason why mutation occurs. Then there's termination, or we can say stopping criteria, that where the algorithm has to stop and find out, okay, fine, am I on the optimal solution or not? So that's basically termination point, or stopping criteria. It's basically the algorithm terminates if the population has converged, which means that doesn't produce offspring which are significantly different from the previous generation. Then and only then it is said that genetic algorithm has provided a set of solution to our problem. Otherwise, we have to start from the very first step, or we can say the second step, fitness calculation. Okay, comments on this is: the population has a fixed size. A new generation are formed individual with least fitness die, providing space for new offspring. And then the sequence of phase is repeated to produce individual in each new generation which are better than the previous generation. Of course, if the fitness is going to be better, then the things would be better. There's a pseudocode which can be used in genetic algorithm. This is a generic pseudocode. Basically, it start, generate the initial population, compute fitness, repeat, and check if the fitness is perfect. If it is perfect, then move, or at least by perfect I mean that basically fitness is the highest fitness, the more compatible it is. Then you have to do the selection procedure, which we discussed what it is in actual, then crossover, then mutation, then compute fitness until population has converged, and then stop. There was this is a sample code, or we can say this is an example. There was a code run in Java which did the same thing. So there was fitness of each and everything, and then the solution was found, and generation was 32. It gives a fitness 5, and genes were basically 111, the 5-bit 1 basically. That's all. If there is any question, you can type in the comment below, and I will be happy to answer that. Thank you very much.